So today we'll have lecture 2. And we're the topic is basically going from inference rules to propositions. By the way, I should say a few things. If you're following the course, whichever way you are, you should be subscribed to the mailing list. If you are not, you should subscribe as soon as possible. The way that the recorded lectures work is that very soon after a lecture, the video will be online. Then there is an editing pass, which usually just cuts off some stuff at the beginning. It's not a very serious editing pass. And then an updated version will be put online. But since it's basically available right away, I don't think I'm going to announce that after today. I'll send an email today, but after today I won't announce it separately. Let's see, what else did I want to say about that? I think, unless there are questions about that, was everybody able to see the video that was posted online? Everybody who tried? So, okay, I think we're in good shape with that. Okay. All right, so I will send one more email about that, but after that I won't separately announce it because generally it'll become available very soon after lecture, so you'd expect it to be up then. Okay, so what we're going to do today is we're going to go from rules to propositions. And before I start, I'm going to do two more examples, actually one more example, and one correction to a previous example, if you will. So remember the last example that we ended with, or the second to last example, was a kingdom for a horse. Okay. Okay, so our representation of that was this. If owns Richard a kingdom, and H is a horse, okay, and we made that persistent, and some person P owns that horse, okay, then Richard now owns the horse, okay, which of course stays, and we have traded it, so P now owns the kingdom, okay. So the schematic variables here I wrote in capital letters are K, H, and P, okay. So you can apply instantiation with any terms that make sense in this context. And the constants, like the R of Richard who says this, is in lowercase. So I'm just going to use that during lecture sometimes to distinguish between what's a constant and what's a schematic variable to make that clear. Okay. Okay. So this actually, if I write the rule like this, doesn't quite represent what we wanted. Okay. And so, of course, with this kind of translation of informal things to formal things, you can always raise multiple different types of objection. The thing here is that this would be a valid inference rule, okay, if King Richard had had kingdoms for horses, okay. But that's not what he said. Okay, he said a kingdom for a horse, okay. So what that means is that this inference rule is still the right thing, but the inference rule can be used only once, right? If he owns several kingdoms, right, he's not going to trade them for multiple horses, right? One to right away, okay, to save his life is enough, okay. So we don't have a good notation for this, and you'll see many examples as we go along where we don't have good notations. And that's one of the reasons why we go from rules to propositions, because propositions gives us notations to make these kind of distinctions. Okay, so I'll just write here that this rule is ephemeral. Okay, once it's used, it disappears. Okay, you can't use it again. If you have a second horse, tough luck, you can't get a second kingdom. Okay. All right. So the other example I wanted to use is a spanning tree. So that's in the graph sort of vein of things that we have done. Okay. So I'll put that over here. And there's another correction I'll have to make here. So remember, we have a graph. So I'm going to draw a particular graph here. something like this. So this was A, B, C, D, E. Okay, now I remember what else I wanted to say. I've been working on the lecture notes, and generally they will take me a little bit longer than the video, okay, because I actually have to write them, okay. So I expect that the lecture notes from first lecture will be available sometime this evening maybe, and the lecture notes from today we'll see, okay. And I will post them online on the schedule page. So the schedule page for the courses should be your main resource for looking up things that I'm publishing. Okay, so this is a graph, and the way we represented this was by an edge relation. So we said edge, for example, between A and B, and we had an edge between A and C, and I'm not going to rewrite everything, okay? And we also had this additional idea that this is an undirected graph. So we had a general rule that says if we have an edge from X to Y, then we can get an edge from Y to X, and this was the rule of symmetry, okay? Okay, so one thing we neglected when we did this is that you also need to keep track of the nodes somehow, okay? Because you want to distinguish this graph from the graph, for example, with another node F over here. Because the graph with F over there is not connected and the one without F is connected, so they're two different graphs, okay? But we have no way to represent whether F is there or not because it's not involved in the edge relation. And we don't track the nodes, okay? So we didn't track the nodes. So we should also have a separate relation, which is a node X. So in this case, it would be A is a node, B is a node, and so on, okay, to track what are the nodes of the graph, okay. Okay. So, for example, the reflexivity rule that was proposed by somebody last time, we could have actually written this if we had thought ahead about this. If X is a node, then we have a path from X to X. And by using this mode, we could have avoided the paradox that we had. You know, if you don't know what the nodes are, we can't just write there's a path from X to X, because we could instantiate with x's which aren't even nodes in the graph. It might be completely meaningless things like horses. Okay. Okay. So when we represent a graph, we want to be careful not just to represent the edges, but also the nodes. Okay. All right. So what we want to write today is an inference system, and thereby, in some ways, almost a program. And we'll make that precise later on in the course what that actually means, to build a spanning tree for a graph. Okay. So the question is, how can we build a spanning tree? So I have to define to you what a spanning tree is. Okay. So the spanning tree for a graph, it has the same set of nodes. Okay. So we'll write. Actually, we don't have F. We want to start with a connected one, so we can really get a tree. So it has the same set of nodes: A, B, C, and D. And we want to take a subset of the edges that connects all of these without introducing some kind of a cycle, okay, into that tree. Okay. So there's different ways to characterize. Does anybody have some ideas on how you can characterize a spanning tree for a connected graph? Yeah?
If you fix a node and then for every other node you specify a shortest length path to the fixed node and then take the first element of each path.
Okay. Okay, I don't quite see that exactly, but there's some characterization like that. Any other ideas? How we can tell whether something is a spanning tree if we have something that's connected? Yeah?
If you remove one of the edges, it's not connected.
Okay, if you remove one of the edges, it's no longer connected. Okay. Does it make sense? Okay. So, so for example, let's see. This thing might be a spanning tree. If I remove any of these edges, I disconnect this because I disconnect two parts, right? And so if it wasn't a spanning tree, for example, if I had that edge which is redundant, okay, then if I remove this edge, it would still be connected, so it would not be a spanning tree. Okay. So that's another simple characterization. We can also do some counting. Can we characterize it by counting? Yeah?
So at most 2 edges on nodes?
At most 2 edges on nodes. Well,
yes, we could of course have a non-spanning.
yeah, so that's also a spanning tree. Yeah?
No, but we have 3 edges on the node.
Yeah, but it's still a tree though.
Oh, yes, so, sorry. Yes,
Yeah.
of course.
N minus 1 edges?
Yeah, so if you have exactly one more node than you have edges, right? Okay, so that's another way to characterize it. It's the last one that is going to be useful for our purposes here. But okay, so we have a graph and we want this to be a spanning tree. So we have to change our representation a little bit in order to make that work. Because before, when we were looking for a path in a graph, we're working just with one graph. Now we're working with 2, basically, when we start and the tree that we want to construct. So we have 2 different ones. Okay. So what we're going to do is we're going to give each of these relations an additional argument, okay, which is the graph that they're in. Okay. So I call this original graph G, and the spanning tree that I want to construct I'll call T for tree. Okay. So originally I have edge AB in the graph G, I have edge HC in the graph C, and I have a nodes in the original graph as well. Okay. The symmetry rule applies to both. So I can say if I have x, y, and whatever graph they're in that same graph, I have the edge going in the other direction. Okay, so it doesn't matter which one it is. Okay, so now we have to think of an algorithm, and then we have to see if we can express this by inference rules. Okay, so a very simple algorithm is we start with one node. We pick an arbitrary one. Okay, so let's say we pick B. Okay, and move it over into the tree. Okay, and now we look at something that's already in the tree, and we see if we can find an edge to some other node that's not already in the tree. Okay, so for example, we can see that there's an edge to C. And C is not already in the tree, so we add that here. Okay. Okay. So then we have to pick either B or C because of the only nodes that we have in the tree right now. Okay. And from one of these, we have to find an edge to something that's a node that's not already in the tree. So if I want to get the thing over there, I would pick, okay, I see there's an edge here. So I put that A in here. Okay. And then let's say maybe I see D, I see this, D is not already in there. Maybe the next thing I see is an edge from A to C, but I wouldn't consider that because C is already in the tree, so I wouldn't add that. Okay. And then maybe I see E. Okay, and I do that. And then do I stop? Well, if I can't find nodes anymore that aren't already in the tree. Okay. Because when I've put all the nodes in the tree, I'm done. Okay. Does that make sense? Very simple algorithm. Okay. I think if you put weights on the edges, then this is a variant of Prim's algorithm, okay, for building a minimum weight spanning tree. But since we don't worry about weights, okay, it's an actually much simpler non-deterministic algorithm. Okay. So now we want to represent this in linear logic. Okay. So I'm soliciting ideas for how to do that. Okay, so what's the first step of the algorithm?
Pick up or the node.
We have to pick an arbitrary node. How would we pick an arbitrary node? Okay, so before that, maybe you should think about what's actually our starting state. Okay, what's our starting state? Our starting state is what we have here, right? Okay, and we'll have to think about which of these things are persistent and which things are ephemeral, okay, in order to make our algorithms work. But certainly we have, these are the facts that we're given, right? These are the edges and the nodes, okay? And when we want to end up with a representation of the spanning tree. So we want the corresponding edges, only the ones that are over here, and we want the corresponding nodes, which should be all of them over here in the tree. Make sense what we're trying to get to? And we want to get to it by inference from this initial state. So we don't need that rule here. Okay, because we're not talking about path. Okay. All right, so how do we start? So we want to pick an arbitrary node. How do we represent that? Any suggestions? Okay, so we have a premise. Well, we don't want to say A because we want it to be arbitrary, so we say X, but it should be in the graph, not in the tree. Okay, so that's the premise. And what's the conclusion? Okay, node X is in T. Okay, do you see how that represents picking an arbitrary node in the graph and moving to the tree? Okay, what that means is that these nodes here, they should all be ephemeral, so they're not underlined, right? They don't because you want to consume that and move it over here. Essentially you move the node from the graph into the tree. Okay. Okay, there's still a problem with that rule, yeah?
You can move all of them over.
Yeah, you can move all of them over that way, right? And you wouldn't have a spanning tree because you wouldn't have any edges at all. And unless your graph is very small, okay, that really wouldn't be a spanning tree. So how would you prevent this rule from firing more than once? Anton?
You can either add a new ephemeral thing to the initial state, or you can make all the nodes like premises that are not ephemeral initially. That's possible.
Okay, so we could do that. I like the other idea better.
One where you add an extra path.
Okay, so let's add something else over here that says that we're in the initial state and make this ephemeral. Okay, so we don't underline it. Okay, and then over here we consume that as part of doing that. Okay, so this has two premises, initial and node xg, and we add node xt, okay, to our database. And because we consume that, okay, that rule cannot fire again. Okay, make sense? Now, if you could also say that rules themselves are ephemeral, another way to say that, well, this is a rule, but we can only fire once. Once you've used that rule, it's gone. Okay, you can't use it again. This is like the King Richard thing, right? He offers only one kingdom for one horse or not again. So if you could say that this rule only can be used once, then we wouldn't need to use this little coding trick here with this initial state. Okay. All right, so that gives us our seed. Okay, so if you apply this, for example, to node A, that would be erased over here. And over here we would write, now we have node A in the tree. Okay. All right, so now we got started. So now we have to figure out, okay, how to describe this process of finding an edge from a node and moving things over in order to build a spanning tree. So how would we do that? Yeah?
You want a node in T and a node in T.
Okay.
Edge between them in T.
Okay, so you want a node X in the tree, okay, and a node Y that's in the graph, okay,
An edge from X to Y.
an edge from X to Y, whoops, in the graph, okay,
And then you have node Y in T.
so we move Y to be in the tree, okay,
X is still in T.
X is still in T, it stays in the tree, okay.
And now you have an edge from X to Y in T.
Okay. Does that make sense? Okay? Any objections to this? Okay, let's worry about, well, we think about correctness, but let's think about first what has to be ephemeral and what should be or maybe persistent. The nodes have to be ephemeral, right? Because we're moving them over. Y has to disappear from the graph so we don't use it again. Right? Once we have moved it into the tree, okay, it should be out of the graph. So that's very important. Is it important whether the nodes that are in the tree are persistent or ephemeral?
You can make them persistent if you like, because once they're in, they stay in.
Yeah, they stay in. We're not going to take them out, so it doesn't matter. You can do it either way. Okay, so we could underline this, make it persistent. That would be okay. There wouldn't be any problem with that. If we did that, then we wouldn't need to repeat this node here, right? Because if that was already there and persistently, then we wouldn't have to worry about recreating down here. But let's keep it this way. What about the edges? Is it important whether the edges are persistent or ephemeral? Let's first think about the graph. Is it important that we remove them when we use them in this rule? No, it doesn't matter, right? Because this is a vertex-oriented algorithm, okay? And the edges are kind of there to connect them, but we're looking at the set of nodes as we're building the spanning tree. And the edges in the tree, does it matter whether they're ephemeral or persistent? No, for the same reason that the nodes in the tree, because we don't actually do anything with the tree, we just create it. We never look at these things. So these could be persistent or ephemeral, doesn't matter. Okay. So it seems like, unless we made a mistake, these two rules together and with this initial state define a way to create a spanning tree. Okay, we just follow the rules. Okay, and hopefully, no matter how we do it, okay, if we follow the rules, we will create a spanning tree. So we should think about why that is actually the case. So actually, let's think about first, why does this terminate? Yeah?
Nodes are decreasing.
The nodes are decreasing? Actually, it looks like they're always the same.
In G.
In G, okay. So claim is that we can apply this rule finitely many times because every time we remove one from G. Okay, so we have one in G here and none in G here. Okay, so this rule can only be applied finite number of times because every time we remove one from G. Okay, if you have a finite graph to start with, it'll be finite. Finite number of steps here. This rule can be applied only once, right? Because either the rule is ephemeral or we remove this assumption here. Okay, so we can in fact say how many times we're going to apply this rule if there is a spanning tree. And we have n nodes. How many times do we apply this rule? N minus 1, right? Okay. Now the question is, why is it a spanning tree when we're done? Okay, or when is it a spanning tree first? What criteria do you apply to the final state to determine if you have a spanning tree? Yeah? If you applied it in, yeah, but we can't tell this anymore because we're done, right?
Right. But if you can, maybe you can modify the rules to keep track of it.
Yeah, we could do that, but I think we can look at the final state and determine whether it's a spanning tree, yeah?
If all of the nodes are in T.
If all of the nodes are in T, or equivalently,
None of the nodes are in G.
none of the nodes are in G, right? If there are no nodes left in G, then we must have moved them all into T, and there are exactly n of them. Okay, so we must have a spanning tree when we're done. Okay. Okay. Now, let's think about our criteria for being a spanning tree, right? We said it has to have exactly one more node than edge. Okay. So how would we be able to see that from the rule that this is the case? That in T, okay, we have one more node than we have edges.
Every time you add a node, except for the first time you add exactly one edge.
Okay, every time you add a node, this is the only rule to do it. Every time you add a node to T, okay, which is here, okay, you add exactly one edge, okay. And this x is actually being preserved here. There's a slight thing you have to maybe worry about, which is the question is, are x and y different? Because if x and y are the same, are you really adding a new node or not, right? So how do we know that x and y must be different when this rule applies?
The fact was consumed before.
Hmm?
The fact must be consumed.
The fact must have been consumed before, yeah. Or if you want to think about an invariant of the state as the thing computes, how would you express that as an invariant of the state? Anton?
It's never the case that one node is in both T and G.
Okay, it's never the case that a single node is in both T and G. Okay, or we could even say something slightly stronger than that.
Every node is in exactly one of T or G.
Right, every node during the whole computation of the algorithm is going to be exactly in T or G, right? It starts out all being in G, and if you have a spanning tree, they will all end up in T, right? Okay, because we move them over essentially one by one, okay? So when you think about these linear logic specifications, it's very important to think about what is the invariant that's being preserved by the rules, okay? Because those are the things you need to reason about to know whether these rules actually accomplish what they're supposed to do, okay? Does that make sense? At least in this example, okay? Okay, so are there any more questions about this example? Okay, so one slight thing we talked about whether these things terminate, okay? And I was very careful to say, well, this rule can only be applied n times. This rule can only be applied, or n minus 1, this can only be applied once. We do have one more rule, which is a symmetry rule, right? And that's a potential source of problem, right? Because we could spin our wheels applying symmetry forever, right? Not really making any progress. So one has to somehow think about why it's okay not to apply this forever, or why it couldn't contribute to a proof, right? If you really wanted to know that this was really represented in an algorithm, okay? Any ideas how one might convince oneself that it's not worth applying this arbitrarily often? Yeah?
Also, we can modify our system such that you don't have to apply it arbitrarily often.
Okay.
You add a reversible judgment, a reversible predicate rather, for each edge, and it gets consumed by the symmetry rule. And so then you can only reverse once. And I think you only need to reverse once.
Okay.
Well, you could just add another rule just like that one, except it takes edge y, x, g.
Okay, you can do that.
So you can't, you can't like flip it because you consume it.
Then you would take this rule out of the system, right? Okay.
Right.
Okay. Now I like this rule though because it automatically says that your graphs are, are undirected. So it's kind of nice to be able to build that directly into the representation. You have another idea?
You can also take, you can leave these rules, but you can say that two proofs are equivalent if they have like repeated application of the symmetry rule, and just talk about the equivalence classes of these proofs.
Okay, you could do that. Yeah. There's another thing one can do. Yeah, you have another idea?
Well, for any proof involving a series of that, we can always replace it by fewer. So we can only conclude the same. Yeah. For any repeated application, we can only ever conclude what's at the outset of the use.
That's right. So we can have a kind of a normal form because either we're using the edge directly or we're using its reverse. And if we're applying another inference rule, we get back what we already had. Okay, so it's kind of a finite model property. There's only finitely many different states that we can reach, and if we track those, then we would stop after we reach all of them. Yeah, another idea?
To the initial rule, we can add a premise, a conclusion, an additional conclusion that says that we're allowed to instantiate the symmetry rule once, because after that we're only using one edge at a time. So if we need to put the edge, we can instantiate the symmetry rule exactly once.
But we might need it for different edges. We might need it more than once. So I think just using it once isn't enough. One thing, so if you keep these things ephemeral, then I think just making sure that we have a finite number of states is a simple way to do it. We could also make it persistent, and we can saturate, okay, the set of edges, okay. So that is, we apply the inference until all the facts that we could possibly derive have been derived, okay. And then stop because any further inference on the edge relation will not give you any more new facts, okay. Yeah?
Well, can you have two copies of one fact? I mean, in general, that might be different from only having one copy of it.
Right. It's extremely important that you have different copies of the same fact. But if these are persistent, okay, if they're persistent, then it doesn't matter whether you have one or two or three or four copies, right? Because if persistent means you can use it arbitrarily often, if you have two things, both of which you can use arbitrarily often, that's no different from having just one. Okay. So a common technique in using these kind of systems is making things persistent and saturating them. Okay. Which means that any further inference on these unrestricted predicates, on these persistent predicates, will give you no more new facts. Okay. Okay. So either we do some kind of, if they're ephemeral, we do some kind of a state enumeration. We make sure that all the possible states have been covered. And if they're persistent, we just make sure that the state is saturated. That applying any rules to any known fact will only give you another fact that you already know. Okay. It's not obvious that all these things work. I just wanted to sort of mention it, plant the seed, and we'll come back to that when we talk about specifically more about operational semantics of these kind of specifications. Okay. All right, but it's quite nice that in this kind of situation, if you want to describe a spanning tree algorithm, all that you need is basically two very simple rules. And it's fairly easy to see that these two actually work. You just need to specify what are the invariants of the state and be careful of proving that these invariants are being preserved. Okay, so now I want to move on. Okay. And talk about propositions. Okay. So far we have gotten by with just inference rules. Okay. And we haven't really written any logical connectives like and or. Okay. We've just actually done inference. Okay. So let's do another example to see why we sometimes want more. I mean, it's nice if you don't need anything more, but sometimes you do need more. Okay. So the example was, okay, if wishes were horses, beggars would ride. Okay, I haven't checked where this is actually from. Okay. I'm not really obsessed with horses. It just happens that two examples I'm using have to do with them. Okay. So the question is, how do we represent this, right? Okay, so let's get a start here. Any suggestions? Okay, the whole thing is rather complicated. Let's break it down into pieces. Okay. If wishes were horses, how would we represent wishes were horses? Okay. Well, it's really your job to ask me then to build a vocabulary, right? So let me actually write you what things we can use. We can say X is a wish, X is a horse, X is a beggar, and rides, X rides Y. Okay, so these are the predicates that I want to use, the propositions I want to use to represent that. Okay? And we'll have to see which things are supposed to be persistent and which things are ephemeral when we actually do the representation. Okay, so wishes were horses. How would we say that? Yep. So it would be wish of X, horse of X. Okay. Now, a wish seems to me a fairly ephemeral thing, right? Wishes that you make and it disappears. Okay. So, all right. So we consume that. Now, a horse is a fairly substantive thing, right? The property for X of being a horse, the horse might die, but still, it's a horse. Okay. So we'll make that persistent. Okay. I mean, there are other possible choices. Okay. So this part here, wishes for horses, would be this. Is this rule a use once rule or is it a persistent rule? Persistent, right?
If, a wish were a horse.
Right. If a wish were a horse, then it would be an ephemeral rule, just like King Richard, right? But since he says wishes were horses, okay, this is a persistent rule, okay? Which inference rules usually are, okay? So that's good, okay. How do we say beggars would ride? Okay, how do we say if, then that? How do we say that?
Well, we want to somehow say, like, if we have that rule,
Yeah.
then
So if we have this thing, let's package it up. This word like a rule, okay. Then,
if beggar y,
okay. So now it's good. If beggar y, let's put that over here. If y is a beggar, okay, then?
y is yx. Well, and I mean, the original saying doesn't say what they would ride.
Okay. Okay, we'll assume they're riding horses. Motorcycles didn't really exist back in those days. Okay, but there's a problem. We can't really say X here. Why can't I say X here?
It's not found.
Yeah, so there's a problem here, right? This rule is schematic in X, right? So this should be applied for any X. So really, I should say for all X, somehow this thing, right? And so that means that, the scope of X is just this rule, right? Which I have to kind of prove, or, which if I want to use this fact, right, I have to gonna somehow prove this. So what does Y actually ride?
It exists.
Yep. It rides a Z, okay, for some Z. Okay. And Z presumably be a horse, but maybe it doesn't matter. Well, actually it should, because if you mention horse here, we probably should mention it here. So I guess we would probably want to say that Z is a horse. And being a horse is like an intrinsic attribute. But, there's this weird thing we have to say for some Z. If I leave out that some Z, what is wrong with that?
For any Z you like.
Right. Okay. Anton?
But then the horse Z could be produced by like another rule, right?
Yeah, right.
So I was going to suggest maybe you can produce in addition to horse as a conclusion of that other rule. You can produce like a special predicate that says that this object has been transformed in this way from horse to horse.
Yeah, that's
And then use it as a premise in the other rule.
okay. Yeah, so we're now getting into sort of more semantic reconstruction that I want to do. Okay. In some sense, right, this thing expresses what this says, right? If wishes were horses means that this rule for all X, right? Because I can use that rule to turn the wish into a horse. Okay. Beggars, okay, so Y better be a beggar before I can apply this rule. Okay. So if wishes were horses and Y is a beggar, then Y would ride. Okay. And it can be any Y because it's arbitrary beggars. Okay, so Y is a schematic variable in this rule. In fact, the only schematic variable over the whole rule. Then it would ride, which means there's some horse that Y can actually ride. Yeah?
So isn't White right in capturing the sentiment
Yeah.
of the sentence? Because the existence of the rule in the premise doesn't say if wishes were horses, right? It says if wishes could be turned into horses. Because nothing obligates you to apply that rule for all wishes.
Okay.
For any wish you like, you can apply it.
Okay. That's a good
So
point.
If
Yeah.
wishes could be horses, beggars could ride, is what that's actually saying.
Okay. Right. It's pretty close though. Yeah.
We also need another premise because the beggar needs to have a wish to instantiate it. So we could say wish Z, so instantiate B for all X. With X for the parameter Z.
No, I think that statement doesn't actually require the beggar to do anything. It just says that, if wishes were horses, beggars would ride. But we don't actually ask
A variable to the premise, with a variable to the premise, an object in the premise that I could instantiate the rule with.
Yeah, when we're trying to produce the same logic, that's what we do, but we're not.
Yeah. So, okay. Well, maybe we should, yeah. I think with this particular saying, we have reached the point of diminishing returns. Okay. So the main thing I want to point out is that there's a lot of things that we like to express. Okay, where the premises and the conclusion of the rules has things that aren't just atomic predicates. Okay, we have to say if wishes were horses, which is a premise for this rule. So we have an inference rule nested inside another inference rule, right? And that's a problematic thing to do, explain what that actually is supposed to mean. We also have the quantification over x, which is not the same as being a schematic variable, but it has a scope because it's only this rule that it applies to. And the z is only the conclusion. We can't leave that out because it doesn't mean that, you know, if wishes were horses, that the beggar could ride any horse whatsoever. Okay, but there will be some horse that the beggar will ride, which is very different meaning. Okay. So what this says is somehow, in order to make real progress in the expressive power what we have, we need to be able to write down as a proposition, okay, an inference rule, okay? And we need to have some kind of explicit quantifiers, because just having schematic rules and variables isn't really the same as having an explicit quantifier, okay? Because you can't really get rid of the quantifier here and move it somewhere else, okay? Okay, so let's start thinking about how to do that, okay? How do we turn inference rules into propositions? Okay, so let's take a very simple inference rules. I mean, wish horse. Okay, so let me just say A ephemeral goes to B ephemeral. Okay, and I want to express that rule in itself as a proposition. Okay, and the notation I'm going to use is something like this: A. Okay, and this is a dash and an O. Okay, it's usually pronounced lolly. Okay, because it's like a lollipop on its side, okay? Or you can say A linearly implies B, okay? So it's almost like an implication, except that it consumes its argument, if you will, okay? Okay, so we're going to try to represent this by this, okay? And that means the following thing. If we know that A implies B, and we have A, then we should be able to conclude B. Okay, does it look familiar? Sort of like a version of modus ponens, right? If you know that from an A you can get a B, which is the contents of this rule, okay, and you actually have an A, you can get a B. That's what this says, okay. So this is also called an elimination rule, okay. But already we're starting to get into a little bit of trouble here, because the question is, I didn't write a judgment here. Which one is appropriate? Should it be ephemeral or persistent? Right? Because this is a proposition. When we use propositions, we have to remark how we're going to use them. Well, there's no right answer. Okay. If this is a persistent rule that we can use arbitrarily often in our proofs, like most rules are, okay, then we would require this to be persistent. Right? If this is an ephemeral rule which can only use once, like our King Richard example, or the examples where we initialize the graph by taking one node out of the tree, by taking one node out of the graph, moving to the tree without that extra initial trick. Okay, it's a rule that can be used exactly once. Okay, then we would say this is ephemeral. It will be consumed as part of the inference rule, because now we have made the transition from A to B, and so this rule is no longer available to us. Okay. Okay. So that seems pretty easy, right? So we just go from this to somehow a arrow B. And if this is an ephemeral rule, this would be ephemeral. If this is a persistent rule, this would be persistent. Okay. But whenever we have connectors, we have to worry about two aspects of it. How do we use it and how do we prove it, right? So we now have to ask ourselves, how do I prove this? Okay, so remember, I won't put the parentheses from now on, because this is something that applies to whole proposition. So it's always everything to the left of it that is qualified by this. Okay, so how do I prove A linearly implies B? Any ideas? When is it okay to say that? We can see when it's okay to use it, but when is it okay to assert it into our database that this should be the case? Yeah?
Well, if we assume A ephemeral and can prove B ephemeral.
Okay, so if we assume A ephemeral, and from that somehow we can prove B ephemeral, okay. There's another way to express this in the vocabulary that we have introduced in the last lecture.
If A ephemeral, horizontal line B ephemeral is a derived rule.
Right. Is a derived rule. Okay, does it make sense? It means the same thing. If we assume A and we prove B, that's how we show that something is a derived rule. We assume A, and from that we prove B. Okay. So A implies B should be the case if this thing is a derived rule. Okay? Okay, so these are two aspects, okay, we always have to think about when we think about logical connectives, how we use them and how we actually prove them. Okay. Unfortunately, we don't really have a mechanism inside the language to do this, because if I actually do this, then it would look like this. Okay, A implies B ephemeral. If A ephemeral, I can prove B ephemeral. Okay, and then I have to put some thing around that. Okay, so now I'm back where I started, right? Yeah?
If that's a derived rule, then this A lolly B should be persistent, right? If that's what it takes to prove A lolly B.
Okay, so that now depends on how you define derived rules. So if all the rules that you use here are persistent, okay, the way we've been doing, then A lolly B should be persistent, right? Because we haven't used anything ephemeral. But if you happen to use an ephemeral rule in there, then this only is true ephemerally, okay? Right? Because once we use a rule that can be used only once, we can only get it once, so we can't use it multiple times. That's a very good observation. We'll come to that multiple times. This trade-off between ephemeral and persistent, it really cries out to be made more precise in the inference system. We don't want to do it for the rules because that's something difficult to manage. But once we get to the propositions, we'll be able to manage it quite easily. Okay. All right. So somehow we're chasing our tail here, right? In order to show how to prove it, we need some notation that we don't already have. Okay. Okay. So we need to somehow change tack. Okay. And so the way we're going to do this is by changing our notation for proofs altogether. Okay. Okay. And in order to motivate this a little bit more, let's think about the coin exchange example. There's nothing persistent there, so we don't have to worry so much about it. Okay. So if you have, let's see, 2 dimes and a nickel, I can get a quarter for it. And conversely, if I have a quarter, I can get 2 dimes and a nickel. Okay. So if I want to now express this using the linear implication, I need to be able to put one proposition on the left and one proposition on the right. Right? So simplifying assumption that there's one premise and one conclusion was really a little bit questionable, right? Because the rules don't look like that. Rules have multiple premises and rules have multiple conclusions, right? So I need to account for that. Okay. So what I need to do is I need to be able to package up the multiple premise and multiple conclusion into one thing, so I can put it on the left-hand side of one of these implications, right? Okay. So if you do ordinary logic, right, you would do this with a conjunction. Make sense? This would say if D and N, well, actually that doesn't really make sense. Bad example. Okay. If you have multiple premise of a rule, you would just take their conjunction. Let's put it that way. Okay. And so there's a similar notation in linear logic. So this rule would be expressed as D tensor N linearly implies Q. And this rule would be as Q linearly implies that I have D tensor N. Okay, and the parentheses here are like that. Okay. And the tensor means that the A tensor B means that A and B are true in the same state. Okay. At the same time. Well, actually, we don't really have time, but in the same state. Okay. So again, we have to worry about when do we prove A tensor B and how do we use it. Okay. So when would you be able to prove A tensor B?
You can prove what A and B.
Yep. So if you have A and you have B, then you can get A tensor B. Okay. And how do you use it? How do you use, if you have A tensor B? Yeah?
If you have A tensor B linearly implies C, then you can derive C.
Say it again, if you have A?
If you have A tensor B linearly implies C, then you store C.
C. Okay, so this really doesn't break down the tensor, right? Because the tensor is still here. It's really a property of implication, right? So if it replaces by any formula, you could do this. It doesn't need to be A tensor B. So we need to find a different way of doing this, of expressing that. Any ideas how else we might express it? Yeah?
If you have A tensor B, and you have A, and you have B.
Like this? Okay, yeah, we just reverse the rule, right? Except, part of the reason we introduced the tensor notation is they wouldn't have to have an inference rule with multiple conclusions. But we still need that here, right? Okay, so we can do it, but it's sort of like the same thing, the problem we had with implication. Here, in order to prove an implication, we needed the notation we wanted to eliminate. And here, in order to eliminate a tensor, we needed the notation that we wanted to get rid of, right? An inference rule with multiple conclusions. So somehow this notation that we have for proof doesn't really seem to work very well. Now let's try another illustration of the fact that it doesn't work very well. Okay, the tensor thing should be commutative because we don't care about the order of things. So we should be able to prove that if you have A tensor B, you can get B tensor A, right? Okay, so how will we do that? Well, we break this down into the components, A and B. Okay. And now they just sit in the wrong place somehow, right? So somehow this is okay. So we eliminate the tensor here and we introduce it here, but it doesn't look right? Because that should be A tensor B. So, so for these various reasons here, the notation that we've been using, which works very well, as long as you don't need any sort of nested things. Okay, you don't need nested implications, a nested assumption, or nested inference rules, kind of breaks down, okay, in this kind of situation. So what we're going to do is we're going to have a new notation that's going to look like this. Okay, so okay. So usually I'll leave out the ephemeral because for the moment we're just thinking about the ephemeral part of things and we worry about the other stuff later. This thing we abbreviate by delta, okay? And this describes the resources or the state that the current state we have. So I'll think about it mostly as resources or current state. And this thing over here is like a conclusion or the goal that we're trying to reach. Okay. And the question we're asking is, if this is our current state, okay, can we perform inference in order to reach this over here? Okay. So rather than always just writing delta, which seemed to fail, okay, we actually write the delta together with some goal that we want to try to achieve. And in many cases, you don't care about the goal, but if you really want to treat this in full generality, then you need to have a goal there. Okay. All right. So let's now start to find the connectives. Okay. Okay. So for each connective, we say how we can use it and how we can prove it. Okay. So how to use it is we specify how to decompose it if it's part of your resources that you have. How to prove it, we show how to prove it on the right-hand side, how to accomplish it as a goal. Okay. So for example, a very simple example is if I have some delta and I have A tensor B and I'm trying to achieve C. Okay, so I'm not going to write EPH there because everything is ephemeral, so I save myself the trouble. Okay, so then I'm going to say that if I have that thing as a resource, that's the same as having A and B separately. Okay, or another way to think, I'm saying it, if I can unpack, okay, a tensor B, which is a single resources containing A and B, into two separate ones. Okay, and the reason I'm doing this is because now I can apply inference rules to A and B. Here they're packaged. I might not be able to do it. Okay. Okay, so this thing is called the left rule. Tensor left. Okay, because it's applied on the left-hand side of this throat style. Okay, to something I can use. So the interesting question is, okay, how do I prove A tensor B? Okay, so how do I prove A tensor B?
You start the resources and prove A and prove B.
Right. So to prove A tensor B, I have to be able to prove A, and I have to be able to prove B. Okay. But I have to be very careful that there's none of the resources that are used on both sides, because they can be used, only once. So the way I'm going to write that is like this: delta prime, and I use delta over here, delta prime over here. And so one convention is that the order of these things never matter. So I can rearrange them to put some resources here and the remaining resources here, and then split them up and use those to prove A and those to prove B. Okay. Resources. Okay, order is irrelevant. And you might guess that if you make order relevant, okay, then you get a different logic from linear logic. You get what's called ordered logic. Okay, it's also interesting, and maybe we'll have a chance to work on this. Think about that later in the semester. This is called the right rule, okay, for tensor, because we're breaking down the tensor on the right-hand side of the turnstile. Okay, so let's do two more, and then let's think about what kind of requirements we have for these rules. We can't just write arbitrarily rules and expect to get a decent system. Okay, so let's start, for the implication, let's start over here. So if I have delta and I want to prove that A linearly implies B, how do I prove that? So what is my Lully right rule? Okay. Yeah?
Delta, comma, AF, turnstile B.
Yeah. This is exactly the reason why we introduced this notation, so we can state this rule. Okay. So to prove that with resource A we could derive B, okay, which is what we want here, with A it could be, well, we add A as a new resource, okay, as another resource. It could already be in there, but we'll have another copy of it, okay, and then have to prove B from that. Okay. So the inability to say that is what brought us down before. Now that we distinguish the left-hand side and the right-hand side, we can do that. We can say that. Okay. All right. And so then the other thing we need to worry about is if we have A or B as a resource and we're trying to accomplish some goals. How do I use A implies B as a resource? Okay, it's still somewhere over there, or maybe I erased it by now.
You prove A to get B, then from it.
Sorry?
You prove A to get B.
We prove A. Okay, so we prove A. Okay. And then we should be able to get B and use it in the proof of C. Okay, so now we need to worry about the resources. Okay, what happens with the resources here? We have to split them into two parts again. So we have to commit part of our resources delta to prove A, and then the remaining resources we can put together with B to accomplish C. Okay? Okay, so the way you use an implication is you get the resource A, then you can use the implication as a rule, if you will, and get B, and then use B together with remaining resources. Okay. Okay. So that's the good start. There are some general principles that don't really depend on any particular connectives. Okay. The first one is very simple. It says that if I have resource A, I can accomplish goal A. And this is called the identity principle because the thing on the left and the right are identical. Right? So that just says that, you know, a resource can be used to accomplish a goal. Now the inverse of that, the converse of that would be, say, if I can accomplish a goal, I'm licensed to use it as a resource. See? Okay, so this one says, if I have a resource, I can prove it as a goal. That's an obvious one. The other one is trickier. It said, if I can accomplish a goal, then I'm licensed to use it as a resource. So how would that work? So if I can accomplish a goal A, then I'm licensed to use it as a resource for proving some goal C, okay, in my quest to solve, to achieve C. Okay. Now I just need to put in the right context here. So what happens with the context?
Split it again.
Yeah, we'll split it again. Okay. I devote some of my resources to get A. That license allows me to use A in order to accomplish C. Okay. So this is the cut rule. And you can see that these two are the converse of each other, right? So if I have a resource A, I can achieve the goal. If I can achieve the goal, I can use it as a resource. Okay. Okay. So that's what we have here. Okay. And the interesting thing is that in linear logic, these are the only rules that you have that don't deal with any particular connectives. Okay. They're generally true, just giving you the connection between being resource and solving a goal, but they have nothing to do with the particular connectives that you have. Okay. Okay, so
Could you replace the cut rule with like a derived rule from implication left and using identity to prove A implies A? A linearly implies A.
okay, let me. You'll have to dictate this to me. So you want to, how do you want it to work?
So just keep the proof that delta proves A.
So we have delta proves A, right?
And I want to prove A linearly implies A.
A linearly implies A, and that's because under the assumption A, you can prove A, which is the identity rule. Okay, and that's the right rule.
Caught in the circle though, because I need to somehow use that fact in context.
Right.
If I
Yeah.
had that, then I could use implication left.
Right. But we don't have that. Right. So you can't replace the cut rule with an easy use of these other two rules. Okay. Let's see. Let's talk about how we make sure that the left and right rules of the connective actually make sense together. Because I could easily make a mistake, in which case I would not get linear logic. I would probably get something that's broken. Okay. So for example, I might have had, instead of the tensor left rule, I might have had the following two rules. I could have said that if I have A tensor B, while I'm trying to prove C, I can get A out. Okay, so why is this wrong? First, intuitively. Why is this wrong? Yeah?
Like losing resources?
You're losing resources, right? Because you're losing B, okay? And so this is not a good rule because you're supposed to have A and B together. The question is, I could have written this rule, right? And maybe nobody would have complained, right? And then we would have gotten into a state where we have this inconsistent logical system or bad logical system. So the question we have to answer, these rules just are not arbitrary, but they have to follow certain internal laws to make sure that that they actually work, are meaningful. Okay. And so if you look at these two principles here, the identity rule and the cut, okay, those are the ones that guide us to figure out whether the rules that we actually write down make sense and are consistent with each other. Okay. So what we want to show is that if we have some compound property A tensor B, A tensor B, okay, we can actually derive A tensor B, okay, and we can do this without using the identity, but using the identity only at smaller propositions, okay, so breaking it down into pieces, okay. So in other words, that's saying that the left rule, we can decompose A tensor B using the left rule in such a way that from the pieces we can reconstitute A tensor B over here on the right. Okay. So that's something we want to check. And something else we want to check is that if you have a cut, so if we're actually using A tensor B because we derived it over here, that license was actually really justified. That is, we can always, when we can prove it here, it's actually okay to use it here without violating any of our logical principles that we want, like preservation of resources. Okay. So we should try to start verifying this. I'm going to index the rule by the proposition A. Okay. So let's start with the first one. Okay. So what we want to check here is that A tensor B, we can derive A tensor B. Okay, how do we do that without using the identity at the type A tensor B? Using it only at smaller propositions. Yeah?
Start with A tensor A, B tensor B, then use what's that? Turnstile, sorry, turnstile.
Turnstile A, B turnstile B, okay.
Then tensor right, then tensor left.
Then we use tensor right at, okay, and we get A comma B, and we get A tensor B, right? So we combine the resources and we build the tensor over here, okay, and now we can apply tensor left. Okay, and these two things are identity, but the proposition that we use it at is smaller. Okay, namely just at the components A and B. So we don't need it at A tensor B because we can reduce it just down to A. Okay, and what you can show is that in general you can reduce, if you do this correctly, identity in arbitrary proposition you can always reduce down to identity at just the atomic propositions. And the atomic propositions are the ones that we had in the examples, like what was it, like horse of X and wish of X, those kind of things that don't have any propositional structure. Right? For those, we still need the fact that if I have it as a resource, I can get it as a goal. But for all the other ones, we don't need that rule because we should always be able to decompose it. Okay. What this says is that the left rule is strong enough, we can get enough information out in order to reconstitute it. Okay. So in this particular case, if I had a rule that just extracts A by itself, okay, then B would have been left over here somehow. I wouldn't be able to complete this. Okay, so I would have come up against an obstacle and say, okay, my logic doesn't really make sense because this principle of identity does not hold. Okay, but okay. All right, and the other thing we should check, and that's what I'll finish the lecture with, okay, is that if you have a cut at a compound type, you can always reduce it to a cut at a smaller type. Okay. And also, let's do it again for tensor. Okay. Let's see. So, okay, I'll make room here. Okay, so how does this work? Well, we have to set up the situation. So somehow I prove A tensor B. Okay, and then I used A tensor B in the proof of C, and then I applied the cut, and I got a proof of C. Okay, and the way I proved that here was by using the tensor right rule, and I got a proof of A and a proof of B, and here I use tensor left and get A comma B in a proof of C. And now I need to put context in. So delta 1, delta 2. This uses delta 1 and delta 2, delta 3. And this is delta 1, delta 2, delta 3 gets me C. Okay? So that's an instance of the rule of cut at the proposition A tensor B. Okay, so the question is it really licensed to actually use A tensor B? Okay, if I prove it only using this rule. Okay, and in order to show that, we want to show that we can reduce this cut at the compound proposition to a cut at smaller propositions. Okay, so the question is, can we simplify this proof somehow so we don't introduce the tensor on the right and the tensor on the left here, but find a more direct justification of C? How would we do that?
Cut at A.
Okay, so we start with delta 1, which proves A, and delta 3 and A and B proves C. So that's a cut at A, and that gives us delta 1, delta 3, and B proves C. Okay?
Then do a cut at B.
Yep, so we have this thing here, B over here. So we can take delta 2 and B and do a cut at B. And then we get delta 1, delta 2, delta 3, proves C. And that's what we needed. Okay, so we have all three of them over here. We have the exact same thing over here. Okay, so it turns out that the left rule and the right rule for tensor are what we call in harmony, okay, in the sense that we can derive the identity principle from the identity principle at smaller propositions, and we can derive the cut principle from the cut principle at smaller propositions. Okay, and that's our test to make sure that the inference rules we've written down actually are meaningful. Okay. Okay, and one can do the same thing for the linear implication, but I'm not going to do that today. Okay. And so what I'm going to continue next time is we're going to think about more of the connectives of linear logic, or more of the inference principles expressed as propositions inside the logic. Okay. And so the big one is the distinction between ephemeral and persistent. Okay. Because we don't have any proposition right now that expresses this, that something is persistent. But you'll see there will be others as well. Okay. So for example, there will be a proposition that expresses that you have no resources at all. Okay. And there will be other resources that have their sort of like disjunction in ordinary logic, that A or B is true. And in each case, we'll think about what it means to how we can use them by thinking about what the left rule should be, and how we can prove them by seeing what the right rule would be. And then we'll see if we can build a consistent logical system out of these pieces. Okay, but even though we changed notation, the fundamental idea of this is still the same as we had last time and in the earlier examples, which is that the main change of view from the ordinary way that you think about logic is that the things on the left-hand side of the turnstile are resources. The things that you have are resources that get consumed as part of inference, okay, which is what you normally don't have in logic. Okay. Okay, other questions? Okay, so we'll hammer some more on this theme next time. Next Thursday, by the way, there's no lecture, just as a reminder. I put it on the webpage because I'll be at Popple. Next Wednesday, sorry. Thank you, Jen. Okay. I always teach Tuesday, Thursday. This is the first time ever I teach Monday, Wednesday, so I have trouble adjusting. So on Monday, we'll talk about some other connectives and the tests that they all make sense. And we'll also examine some more examples where we actually use the expressive power that we have here. Okay. Okay.